6.3 Review of ODEs and classification of fixed points at local, linearized, separable level. Let's begin by shifting the origin in the phase diagram to be at a fixed point of interest and explicitly write the velocity function in terms of an expansion in position function. See equation 6-7. Since bold italic V of bold 0 equals 0 at fixed point, where A is a non-singular real matrix. Following the notation of Percival, let. See equation 6-8.
For sufficiently small bold italic R of bold italic X bold italic Y bold, we get only the linear term in bold italic R bold equals a bold italic R. We would like to diagonalize the matrix A, and from there have a standardized evaluation of the fixed point behavior. To accomplish this, consider the transformation to new coordinates bold italic R of bold italic X bold italic Y bold equals M bold italic R bold equals B bold italic R, where B equals MAM to the negative 1 power. 3 cases result. Case 1, the eigenvalues of B are real and distinct, in which case bold italic X bold equals lambda sub 1 bold italic X bold italic Y bold equals lambda sub 2 bold italic Y. So, see equation 6-9.
If we have lambda sub 1 is less than lambda sub 2 is less than 0, then we have a stable node. Likewise, lambda sub 2 is less than lambda sub 1 is less than 0. If we have lambda sub 1 is greater than lambda sub 2 is greater than 0, then we have an unstable node. Likewise, for lambda sub 2 is greater than lambda sub 1 is greater than 0. If we have lambda sub 1 is less than 0 is less than lambda sub 2, we have an unstable node, a hyperbolic point. And similarly, but with arrows reversed, if lambda sub 2 is less than 0 is less than lambda sub 1. Case 2. The eigenvalues of B are real and equal. There are 2 subcases. Suppose B equals C equals 0, then must have lambda sub 1 equals lambda sub 2 is less than 0, B equals C equals 0, known as the stable star. Likewise, the lambda sub 1 equals lambda sub 2 is greater than 0, B equals C equals 0, case is the unstable star. If, on the other hand, C is not equal to 0, then have. See equation 6-10.
With solution. See equation 6-11. The phase curves for this case describe an improper node that is stable if lambda sub 1 equals lambda sub 2 is less than 0, B is not equal to 0, C is not equal to 0, or an unstable improper node if lambda sub 1 equals lambda sub 2 is greater than 0, B is not equal to 0, C is not equal to 0. Case 3. The eigenvalues of B are complex and conjugate to each other. Lambda sub 1 equals alpha plus I omega equals lambda sub 2 asterisk. Suppose the eigenvalues are pure imaginary, alpha equals 0, this gives rise to an elliptic point, with rotation clockwise or counterclockwise according to the sign of omega. Suppose alpha is less than 0, we then have a stable spiral point, with rotation according to sign of omega. Likewise, if alpha is greater than 0, we then have an unstable spiral point, with rotation according to sign of omega.
Thus far, we've identified the different fixed point behaviors. For first-order systems, all motion tends to either a fixed point or infinity, so we have a complete taxonomy with what has been described thus far. For second-order and higher systems, this is not necessarily the case. The explicit example of the limit cycle is given next, with strange attractors left to a later section where we discuss the transition to chaos. In our identification of fixed point behavior, we've overlooked the possibility of a fixed subset that is not simply a point. Even in second-order systems, these can occur, resulting in the classic limit cycle phenomenon. Consider the following explicit case given by in this regard. Suppose we have a system separable in polar coordinates according to, see the next equation. The circle R equals R is invariant, and for motion in the neighborhood of the cycle it is either a strong attractor, stable, or the reverse, e.g. unstable, with flow lines reversed.
See the equation shown. Example 6.7. Unstable spiral and stable limit cycle. For small x sub 1 x sub 2 the system. See the next equation. Reduces to a linear system which has a center at 0, 0. Show that the nonlinear system has an unstable spiral at 0, 0. And a stable limit cycle at R equals 1. Solution. For both small and thus small, have. The latter result establishes that this is an ellipsoid point, Percival, with center at 0, 0. Let's now examine the R behavior. Start by grouping. See the equation shown. This can be rewritten.
A limit cycle is indicated at, to confirm, in the neighborhood of. Now let's consider when R is near 0. For R near 0 we have R approximately equals R squared, and since we start with R is greater than 0 we will clearly have R is greater than 0, thus it spirals outwards. Example 6.8. Elliptic fixed point, C. Percival, P41. Show that the origin is an elliptic fixed point for the system. See the next equation. Further, show that A. The circles are equals 1/n, n equals 1, 2, are phase curves. B. The trajectories between any two consecutive circles spiral either away from or towards the origin. C. The phase curves outside of R equals 1 are unbounded. Solution. We have an elliptic point with center 0, 0, if x sub 1 equals negative x sub 2 and x sub 2 equals x sub 1, precisely the case as R goes to 0. A. When we substitute R equals 1/n, we identify these phase curves as concentric circles.
See the equation shown. B. Grouping the equations to get a total derivative. Thus we have the sign of R changes according to the sign of pi divided by R. If we group to get the second solution, we would see that group spiraling inward. Between any two consecutive circles R equals 1/n, the sign will flip. Thus, the R equals 1/n curves will be limit cycles. R is less than 0 if above and R is greater than 0 if below the R equals 1/n limit cycle. See, if R is greater than 1, then the sign of pi over R is always positive, thus R is always positive, spiraling outward. 6. Point for linear systems and the propagator formalism. Case 6 above is an example of a non-autonomous system, where the velocity function is an explicit function of time. For a linear second-order system, possibly by perturbation approximation to be discussed later, we have the equations. Equation 6-12. Let's take B of t equals 0, for which a 2 by 2 matrix-valued function exists that allows us to write.
See equation 6-13, where the matrix bold italic K of t sub 1 ton sub 0 is the propagator from t sub 0 to t sub 1. Note that the propagator satisfies the Chapman-Kolmogorov relation, occurring in information theory. See equation 6-14. The propagator matrices in this representation need not commute. Discussion about the Chapman-Kolmogorov and the Definetti exchangeability criterion is made in later sections: quantum variance in Book 4, stat-mech variance in Book 5, and information theoretic issues in Book 9. Numerous results are conveniently accessible in the propagator formalism. To get started, let's establish a relation between known solutions and the propagator matrix to arrive at a quick transformation to the propagator formalism. Following the discussion of, let's start with writing the two-element column vector as a mixture of any pair of solutions.
See the next equation. Let's now focus on the case where, at t sub 0, we have bold italic R sub bold 1 of t sub 0 equals the 2 by 1 column matrix 1 0 and bold italic R sub bold 2 of t sub 0 equals the 2 by 1 column matrix 0 1, c sub 1 equals bold italic x of t sub 0, and c sub 2 equals bold italic y of t sub 0. See the equation shown, where the matrix values are chosen as indicated, given the special solutions chosen at t sub 0, and to be consistent with the eventual propagator form that is obtained.
See the next equation. Thus, see equation 6-15. Consider case 2 above, where u of q equals positive 1/2 a q squared, the linear oscillator. The solutions were found to be, see equation 6-16. Let t sub 0 correspond to t equals 0, we then have for solution 1.
See equation 6-17, where we meet the special form needed if delta equals 0 and a equals 1. Similarly, for bold italic R sub bold 2 of t sub 0, we choose delta equals 90 and a equals 1 divided by negative m omega. Thus, see equation 6-18. Notice that det bold italic k equals 1, thus describes a mapping that is area preserving, as is necessary for Hamiltonian systems. For the K matrix we have similar stability evaluations as before for B matrix. Further discussion along these lines can be found at